After univariate regression, we do multiple regression. The basic idea is perfectly simple. We just add more x variables into our code. It's really very simple. I mean, the math gets more complicated. That's why it's sort of segregated in the curriculum. But in this course, we've left off most of the math complications. Leave that to the computer to muck around with. In the formula, we're going from y equals beta naught plus beta 1 times x1 to y equals beta naught plus beta 1 x1 plus beta 2 times x2 plus, on and on and on to beta k times xk. We're just adding a bunch of subscripts. When writing code in R, instead of lmy twiddle x1, we use lmy twiddle x1 plus x2 plus x3. Just go crazy with it. Writing code, it's pretty simple. There are a few details to keep track of. For instance, when doing hypothesis tests on each coefficient, the t-test is going to have n minus k degrees of freedom, where n is the number of observations and k is the number of variables in the regression. But again, the computer keeps track of that. If we have relatively few observations, then we might need to be careful about how many variables are in our regression. But, other cases, we got thousands of observations, such as, the labs we're doing in class. We have enough obs, we can add lots of additional x variables and just go crazy. In multiple regressions, we still interpret the coefficients on the x variables as the slope, but it's how much the average value of y would change when that one particular x variable changes, but all the others are held constant. If you remember multivariate calculus, that's just saying the coefficient estimates are the partial derivatives. Beta estimate is partial y, partial xi. Also from multivariate calculus, you might remember, at least locally, any continuous differentiable function can be approximated by a linear function. So it might seem our assumption of linearity is quite stringent. On the other hand, you can make a case that it's going to be true for quite a pretty generic class of functions, at least within a local area. Often we include dummy variables among the x variables. Dummy variables are either 0 or 1. The coefficient on the dummy is the change when that dummy goes from 0 to 1. In R or other statistical packages, they report the coefficient estimates, standard error of each, the t-stat, which is the ratio of the coefficient to the standard error, and the p-value, which is the area of both tails with degrees of freedom, n minus k, calculated from that. You should be able to understand where the computer getting those. It's not sorcery, it's just math. Some notation details. The model fits y to be beta naught plus beta 1 x1 plus beta 2 x2, so forth, plus e, the error. The fitted values are denoted y hat, calculated from the estimated coefficients, each with a hat notation. Beta naught hat, beta 1 hat, etc. The residuals are what's left over. We subtract y minus y hat, where y, minus each coefficient, estimated coefficient, times the x values. As with the univariate case, the mean of the errors is going to be 0, because that's how the intercept term is defined. Here's a simple example using BRFSS data. Using the BRFS data, we want to explain BMI for each person with age, education, and how many hours of sleep they get. In R, we create an object, here we'll call it model OLS, defined by the LM call for linear model. The formula is the format y twiddle x1 plus x2 plus x3, and data is used as that's the full BRFSS 22. If you did it for the people in the tri-state area or the ACE subsample, that would be different data to be used. These are the results that R spits out. Look down those coefficient terms. Each line displays the coefficient estimate, standard error, t-stat, p-value. First line is the intercept term, which usually more of a nuisance term. Each term then gets stars if the p-value is very low, because that indicates the coefficient is likely different from 0, if all the assumptions are correct. In this model, people who sleep more have a lower BMI. Education doesn't have much influence other than the highest levels, but age is definitely significant, with a hump that we've seen before. So the highest coefficients are in the 45 to 54 age range. In R, we have a lot of handy ways to work with the output from the LM call. Once you estimate the model, as the previous slide, you can access various segments of the output. The coefficients, model OLS, bring the coefficients. The fitted values of model OLS bring the fitted values, the y hat. The residuals, the difference of y hat from y, that gives those. Conf int gives you the confidence interval for each of those coefficients. The plot gives a bunch of interesting plot. ANOVA gets you the ANOVA tables. Yeah, it's not exactly mysterious notation. So you can generate predicted values for particular cases. Might want to ask, what is the predicted BMI of somebody age 30 to 34 with a high school diploma, gets 8 hours of sleep, and R will tell me exactly what is the predicted value in that case. It's often a good way of assessing if the model seems reasonable. It's also a way to generate counterfactuals. For instance, if I wanted to know how much variation would remain if I took out age effects, could do that. Note it distinguishes between confidence intervals and prediction intervals. If the value I'm trying to predict is within the observed X, then I would use confidence interval. While if the prediction is X outside the interval, then it's prediction. It's important in time series, but not usually relevant for the micro data that we're using here.